Of all the stars in the heavens, only one is vital to our planet. It has dominated the Earth for 5 billion years, providing heat, light, and energy, sustaining life, and taking it away. While the ancients viewed the sun through a veil of myth and legend, we are just beginning to understand the mysteries of this powerful stellar engine.
There are several factors which make studying the sun exciting. Many, many times we see something that nobody has ever seen before because we have new telescopes that are pointing at this star, because we see this hour-to-hour change. We can see the eruptions happening before our eyes. We can see all kinds of things that we never expected.
We've been studying the sun telescopically now for 4 centuries. We've been studying it from space with an array of very sensitive X-ray, ultraviolet detectors for 2 decades. And the sun keeps surprising us.
Perhaps the most unique aspect about the sun for us compared to other stars is its closeness to the Earth. It is 330,000 times closer to the Earth than the next nearest star, at least the next nearest star that we have detected.
The sun is not really a special star, except that it's our star. But we can, from studying it, see that it exhibits certain behavior which you probably would not notice looking from far away.
Well, in spite of the fact that we can observe the sun in great detail, and in spite of the fact that we have a pretty good understanding of what the sun is doing, there's still many details and many fundamental things we don't understand about the sun.
As we continue to look deeper into the sun's intriguing nature, we find ever more questions to ask and innovative tools to answer them.
Backwards towards us, rotate around. To your left, continue left.
Look who's here. Hi. I like your pictures of me. Got any more?
Oh, yes, lots. Roll 6. The camera's one of our main tools.
The original work observing the sun was done with single glass plates, like observing stars. Then movie cameras were developed in the 30s, and people began to take movies of the sun so they could get the dynamics of what was happening. Then video came in, and video had the advantage that we could get quantitative measurements of the brightness level we were looking at. They were also sensitive to different wavelengths. So we gradually introduced video cameras, and then the cameras called charge-coupled devices, CCDs, came in, and those give us very high-resolution digital images.
One of the instruments that solar astronomers use extensively is a filter. There are varying different kinds of filters, and here at Mount Wilson at the 60-foot solar tower we use a magneto-optical filter. We use this filter to give us a very narrow portion of the sun's spectrum. In the sun, we have a large number of photons which strike the mirrors or lenses of our telescopes, but by the time we pass that solar beam through a large number of filtering components, we also end up in many cases with a relatively small number of photons out the back end of the instruments. One of the principal tools that solar astronomers use behind their telescopes is the spectrograph. In a modern spectrograph, a portion of the instrument called the diffraction grating is used instead of a prism to disperse the solar spectrum into its constituent wavelengths or colors. Once the spectrum has been dispersed, then it is possible to study very small portions of the solar spectrum so that we can look at the amount of intensity that we see either between solar absorption lines, in the wings of solar absorption lines, or in the cores of those solar absorption features.
Using this technique, in 1908, George Ellery Hale was able to employ the Zeeman effect to demonstrate the existence of strong magnetic fields on the sun.
The Zeeman effect is a splitting of spectral lines into multiple component parts in the presence of a magnetic field. Not only are the spectral lines split into components by the presence of the magnetic field, but the amount of the splitting, that is, the size of the splitting in wavelength, is directly dependent upon the strength of the magnetic field. We use our solar telescopes in combination with spectrographs or filtergraphs to make measurements of either the intensity across the visible disk of the sun in certain spectral lines, or in the solar continuum between the spectral lines, or we make measurements of the line of sight motions across the solar surface through the use of the Doppler effect. Once we've taken these time series of images, we have to process them in such a way that we can then study the solar oscillations from these remote sensing images.
That is called the science of helioseismology. What we observe is the constant noise which is going on there all the time, excited by all this sloshing around on the surface. If we analyze these waves, we now can see what some of the physical conditions are below the surface. And that has enabled us to test all of our models of what was going on the inside of the sun.
One of the most exciting aspects of my own personal research in helioseismology occurred very unexpectedly during my PhD research. While trying to study the spectra of our solar oscillation modes that I had obtained at Sacramento Peak Observatory, I found that the frequencies of the waves that were traveling in the same direction that the sun rotates, the so-called prograde traveling solar oscillation waves, had a different frequency than the waves that were traveling in the retrograde or opposite direction. And so it was only with a serendipitous discovery that the frequencies were split by the traveling nature of these waves that we were able to infer that we could make measurements of the surface or near-surface rotational properties of the sun.
Through such innovative techniques, we've discovered intricate details about the sun's structure. Yet answers to our emerging questions are limited by our tools of observation.
The major drawback with observing from the surface of the Earth is the darn air that we have to breathe to live, because while the air appears transparent, it really isn't completely transparent. In certain wavelength regions, it's totally opaque, so we can't see the ultraviolet. Of course, we're rooting for the ozone layer to be destroyed so we can look through it, but I think most people don't want that. But probably an even more serious drawback is the very small twinkling of anything we look at through the atmosphere because of the small changes in temperature and density, and that results in what we call seeing. The images that we look at are shimmering and dancing.
The turbulence of the Earth's atmosphere distorts the images that we see. This is why astronomers, solar astronomers, have recently started flying small telescopes and complexes of instruments on board free-flying satellites, Earth-orbiting satellites, and on board the space shuttle.
From the earliest space missions, our view of the sun has changed dramatically.
Space-based observations of the sun actually began with the first planetary missions, which were flown in the early 1960s. One of the early Mariner missions to Venus confirmed the existence of the solar wind, the outpouring of material from the sun and the escape of the corona into space. The next major advance was associated with Skylab.
Skylab is the first space project that made real X-ray movies of the sun, and those showed some very interesting features. The X-rays trace out the corona, the upper atmosphere of the sun, the hot, tenuous gas, and one could really see it very clearly as to what's going on and some of the dynamics and structure, which was unknown today.
Rotate around to your left. Pitch down. I got you in sight.
Building on Skylab's success, NASA launched a similar mission. In 1980, during a period of high solar activity, the SolarMax satellite was put into low Earth orbit.
It consisted of a single spacecraft in Earth orbit, and it had a lot of the kinds of instruments that one associates with ground-based solar observatories, except for the fact that the region one goes into space to look at the sun is to look at the short wavelengths that are normally cut off by the Earth's atmosphere.
In October 1991, the Ulysses spacecraft embarked on a mission to further unravel the mysteries of the sun. Named after the Greek hero of the Trojan War, one legend of Ulysses tells of a warrior who journeyed to the uninhabited world beyond the sun. Like the mythical hero, the Ulysses satellite will journey to regions never before explored from Earth by passing directly above the polar regions of the sun.
Polar regions are expected to be much simpler than the equatorial regions, which should make it easier for us to understand the physics involved, and furthermore to relate the kinds of phenomena, the kinds of structures we see in the polar regions to things on the sun. There are good reasons for believing that conditions in the polar regions are very different than they are near the equator. We'll be very surprised if we don't find some new discoveries and some new surprises, as you might expect when you go into a new region of space.
While exploration of the sun's deepest secrets reaches its pinnacle with the Ulysses mission, it also marks a significant milestone in our understanding of the sun's structure. From the Earth, the sun can be seen as a radiant disk, yet it has an intricately detailed structure from its inside out.
The sun is a star, and it's made up almost completely of hydrogen and helium. A little less than half of it is helium.
Unlike the Earth, the sun doesn't have well-defined distinctions between the different regions. There's not like solid interfaces like there is in the Earth, but nevertheless one classifies different layering structures in the sun.
At the core of the sun, under the crushing weight of its own gravity, temperatures exceed 10 million degrees on the Kelvin scale, hot enough to produce the thermonuclear reactions that power the sun. Surrounding the core is the radiative zone, where energy generated in the core slowly radiates outward. Still further out is the convective zone. Here, turbulent gases carry heat to the outer layers of the sun through the process of convection.
The convection zone of the sun is thought to extend over about the outer 27 or 30% of the sun's radius. The convection zone is given its name because in that portion of the solar interior, the gas is very unstable and is bubbling or boiling.
And the convection zone goes all the way out to what the photosphere, the visible surface of the sun, where, again, the energy transport changes from convection to radiation. And now there's a fairly well-defined boundary.
The photosphere is given its name because this means the light sphere. It is, in fact, the portion of the sun where the photons that we see the sun with originate. The photosphere is not one simple layer of the sun. It's actually a range of depths that are about 300 to 500 kilometers in thickness.
That gas changes from being fairly opaque, so there's a fuzzy surface of a couple hundred kilometers, 100 miles. But the sun is 150 million kilometers away, so we see that as a sharp edge and as a distinct surface. The photosphere that we look at has a small-scale convective phenomenon that we call granulation, and there's a somewhat larger scale phenomenon which is supergranulation, and these scales reflect the convection that's going on down below the surface.
What these granules actually are the very tops of the uppermost zone of convective bubbles. What we are seeing are the portions of the solar surface where the heated gas is rising at the centers of those bubbles, and then we're seeing the edges of those bubbles where the slightly cooler gas then starts to fall back inward into the convection zone.
The transport by convection is very similar to what you see in the desert in the summer. The ground gets heated very hot. The heat has no place to go, so it heats up air and you get dust devils and you get a lot of convection which bounces your airplane around and does things like that.
The next portion of the sun's atmosphere is above the photosphere. This is called the chromosphere of the sun. It is much less dense than is the visible surface layer of the sun, and therefore we can only see the chromosphere either during a brief moment at the beginning or ending of a total solar eclipse, where it is seen as a reddish or pinkish crescent, or we can see it from Earth orbiting spacecrafts when we use an instrument called a coronagraph.
These layers get hotter as we go upward instead of colder. For many years, people thought that as you went out from the sun, it just got colder and colder and colder as you ran out of energy. In fact, the chromosphere is several thousand degrees hotter than the surface.
And in a distance of about 200 kilometers, or even thinner than the photospheric layers, the temperature rises to the order of about 500, 600,000 degrees absolute. This very thin region is called the solar transition zone. It is that portion of the sun's atmosphere that is directly above the chromosphere. The top of the solar transition zone then begins to merge into the bottom of the next layer of the solar atmosphere, which is called the solar corona.
The corona has a very low density. That density is about 1 billion times lower than the photosphere. It is probably for that reason that it is so darn hot, because you're having energy flowing out from the sun, and the density being so low, it cannot emit that energy. So it heats up until it gets to a high enough temperature that it emits it.
Eventually, the corona merges into what's called the solar wind. The solar wind is that portion of the outer atmosphere of the sun where the ions, because it's almost a completely ionized plasma, are no longer gravitationally bound to the sun. Instead, these ions begin to gain enough energy that they actually become liberated from the sun's gravitational field.
And the heat is so great that once I get out to about 5 solar radii, this stuff has to start flowing out. And it flows out toward the Earth, it flows out way past Jupiter, and Voyager is still stuck in it.
From the solar interior to the turbulent solar atmosphere that extends beyond the outermost planet, we've discovered much about the structure of the sun, but we have just begun to uncover the enigma of its violent behavior. While we seek to provide more detailed answers about the sun's tumultuous activity, we have known for centuries that the sun is far from being the pristine and tranquil orb the ancients believed it to be.
When Galileo first looked at the sun around 1600, he found spots, and one can find books published a few years later which had magnificent drawings of the sunspots. The sunspots are regions of intense magnetic fields. Kind of surprising if you think of a star. Now, why would these little spots be there?
Galileo and the many astronomers that followed observed that these intriguing dark spots seemed to move across the surface of the sun. Indeed, they were observing the rotation of the sun itself. By exploring these spots, they answered some of the questions that have helped shape modern astronomy.
Because the sun is not solid, it's gaseous, it doesn't need to rotate uniformly like a solid body, and it doesn't. The equator rotates more rapidly than the poles. The equator rotates roughly once every 25 days, whereas the poles rotate once every 35 days.
If we freeze the dynamic sun just for an instant, we can artificially line the spots from pole to pole like runners at the start of a race. When the rotation begins, the sunspots at the equator slowly pull ahead of those at higher latitudes. After about 25 days, these equatorial sunspots complete a full rotation, leaving spots in the mid-latitudes to finish a few days later, and the polar latitudes to finish several days after that. While sunspots reveal the curious motion of the sun's rotation, the spots themselves have held their own secrets.
They come and go, sometimes change in shape every few days. They travel across the surface of the sun and mark the sun's rotation of about 27 days. And every 11 years, they increase and decrease in number. It wasn't until 1908 when George Ellery Hale, who founded this observatory, went to the 60-foot solar tower and used that telescope to look at a sunspot in detail and found out that there are intense concentrations of magnetic fields.
There are about 3,000 Gauss, which means that it's about 3,000 times stronger than the magnetic field here at the surface of the Earth. So if you look at the field that moves your compass needle around, the field in a sunspot is 3,000 times greater. Almost all of the activity that we see on the surface of the sun is sunspot related. Sunspot will appear and have a large number of eruptions and flares. We're very much interested in what kind of sunspots generate solar flares, because solar flares are a tremendously energetic and interesting phenomenon.
The flares are material that's actually been lifted from the surface of the sun and is being ejected into outer space. As the magnetic fields change on the surface of the sun, there's also a wind emanating from the sun. The magnetic fields in the wind are actually being carried away by the gas in the outer corona of the sun, the very outer part of the atmosphere. So there's magnetic field that is not only inside the sun, but is carried to the surface, makes its way into the solar wind, blows towards the Earth and interacts with the Earth. Often they end up interacting with the Earth's environment and cause things like aurora. If you go out at night, that's just the energy being released from the solar flare, the material from the sun interacting and releasing its energy into the atmosphere of the Earth and causing some molecules in the atmosphere to glow.
When you have a big storm on the sun, a big eruption, a solar flare, or the passage of what we call a coronal hole, you can have big disruptions of the Earth's magnetic fields. These rapid changes will induce a voltage in a 1,000-mile power line that they wouldn't induce in just a 2-mile power line. The voltages are a surprise to the power companies, and they kill the circuit breakers, because the circuit breakers are there to keep these big voltages from burning up the transformers. If the shutdown isn't expected, then you can get a power outage.
We can't predict when flares are going to occur. Prominences are related. They generally don't lift off the surface, so you might see a beautiful, huge arch of material, but it won't leave the surface. It's still bound. It doesn't have enough energy to exit the sun's gravitational field. So they're related. We can't predict either one.
Because sunspot-related activity can have a damaging effect on Earth, much effort has been invested in trying to understand the sunspot cycle.
The kind of explanation that has been offered, there's something called the Babcock cycle, which suggests that the spots are enhanced by the differential rotation of the sun.
So in the 1950s, Horace Babcock outlined a picture of what we call the dynamo, sort of a regenerating process of renewing the magnetism every 11 years on the sun.
The Babcock model suggests that at the beginning of a cycle, the sun's internal magnetic field runs in straight lines between the poles. As the cycle progresses, differential rotation causes individual field lines to bend and be pulled around the sun. As the equator continues to rotate at a faster rate, the magnetic field eventually runs parallel to the equator. Meanwhile, rising and sinking convection currents twist the fields into rope-like structures that rise toward the solar surface. These magnetic ropes can break through the surface, creating pairs of sunspots that can last for a few weeks. The continued winding causes later sunspots to appear closer and closer to the equator.
The Babcock model of the dynamo helps us understand that the interior of the sun is quite important in this process, as well as the interaction of the magnetic fields with these motions in the sun. But it fails to explain why every few centuries this 11-year cycle seems to shut down.
So no one knows why it would turn off for any period of time like that. Nevertheless, it appears to have done so. And there are thoughts that because the solar cycle turned off, that changed the luminosity slightly, and that led to what's called the Little Ice Age in the northern hemisphere. The Thames froze over in England, which it never does and hasn't done since, things of that nature.
So if you look back at those agricultural records or shipping records over the seas, see that there was a lot more sea ice in northern Europe. The crops failed dramatically during the latter part of the 17th century because the growing seasons were shortened.
That makes you think about what happens to the climate of the Earth. The Earth is extremely stable. If you heat it up, it starts radiating a lot faster. So it takes a big change in the sun to make for a change. You have this blanket of atmosphere around us that protects us. So on the short term, all these suggestions of gloom and doom, such as global warming and things like that, or cooling, or whatever you can dream up, nuclear winter, are probably exaggerations for this very stable atmosphere. Over a very, very long run, the sun is eventually going to be very hot and things will get uncomfortable here. And everything we look at says, yeah, this is really going to happen. You know, that's just the reality we have to face. So we are transient. We may only last a few billion years, but that's a long enough span, I guess.
While the sun has sustained the Earth for 5 billion years, we know that like all stars, it must one day yield to its own mortality. From ancient stargazers to modern astronomers, we'll continue to explore the sun's incredible power and mystery.